Okay. So moving on. So just for background, obviously we're all interested in the dynamics of soil moisture, and the interest in scale is one of my primary interests. And these things vary with topography, soils, and management, as some others have already pointed out. With various sensors, you get different support scales. And as Tyson mentioned, there's an advantage of these cosmic ray sensors for multiple reasons. The other issue that I'm not going to address fully, but want to touch on, is temporal integration. We talk about accumulating neutron counts with sensors. They're reported as a rate, but really it's an accumulation. So I'll talk about that a little bit. Forward. There we go. Whoops, I went forward twice. Yeah, so today I really want to talk a little bit about calibration of cosmic ray neutron sensors. We use dielectric sensors for the ground data as well as some gravimetric data, and explore variability in these calibrated parameters. Something I don't see a lot of this in the literature. I know some of you probably have grappled with this, but it's something that I'd like to discuss, and also discuss what is the precision and uncertainty of the measurements that we're getting, because I do think cosmic ray sensors are so valuable in terms of support scale, in terms of depth of measurement, and in terms of, like Tyson said, you can just put this out in the middle of a field, and we've had very reliable systems for many years. So this is my little network in eastern Colorado. We're looking to the west. So you can see at the bottom of this slide, it's about a 10-kilometer scale. So speaking of scale, quite a bit of variability within, say, a 9-kilometer SMAP or a 36-kilometer grid scale to the, does this have a pointer? Sorry. Does this point, or do I use my finger?
The clicker?
Yeah, that's okay. I'll just describe it. Okay. At the top of the slide is the Rocky Mountains. And so we have source water areas, snow-fed rivers flow onto the plains. We're here in Fort Collins, that little green square, and we're in this transition between mountains and plains, and all of the water comes through us, and users are largely in the city area, that front range, we call it. And if you look at the map, you can see transition from the urban to irrigated agriculture to dryland agriculture, which is our Drake Farm site, and up to rangeland. So I'll be talking primarily about the Drake Farm. This come out? It's pretty dark. Sorry about the font. So it's semi-arid climate. It's a 56 hectare watershed within a wheat fallow system. And it's been converted from that wheat fallow, which I'll show you a map of, to CRP, or a conservation reserve program, with perennials in 2013 and 14. We do have spatial measurements going back to 2001 is for soil moisture and soil temperature, as well as several other variables, micrometeorology, and other studies that we've done at the site. In the middle, you can see our cosmic ray system. That's Rob Erskine working with it. We also have a mobile time domain reflectometry system that we use to collect spatial data. And then within the field, we have in situ sensors that are just capacitance sensors, and I'll show you a map of those. So this is a map. The colors are topography. Blue is high and red is low. So the watershed is defined by a flume at the edge of a field. The yellow are the strips of wheat. They're in a wheat fallow rotation. So we put two transects of the Centec capacitance sensors. These are the green dots there. And so we have dynamics. Those are hourly data. We started collecting half-hour data, but that was too much. The cosmic ray sensors are shown here, and I'll talk mainly about the one on the north side. That's the cosmic ray neutron sensor. This is just to show you an example of, there is variability. These are normalized over many sample dates, so we can look at spatial patterns more useful as a snapshot. And then I wanted to talk about the temporal dynamics of moisture in the profile. So if you look at this middle column, we have the E1, E2, I should have pointed out, we're in the northwest corner of that field. And E1 here is in a fallow And as Tyson mentioned earlier, actually, that's accumulating water from precipitation, while the wheat phase in the other strip is declining generally. This was an interesting period because we had 2 years adjacent to that had strong wetting fronts in the spring and winter. If you were here in 2003 and remember a meter of snow in Fort Collins, that was that wetting front followed by some summer rain. But what you can see is even with that strong wetting front, it didn't penetrate really much past a meter. The 2 years later, we did get a wetting front that it went all the way down, but I just wanted to point out that dynamics are not extremely fast in the semi-arid climate. A lot of storage available. So cosmic rays, what are we measuring? Very briefly, we have these incoming cosmic rays, protons from space, and those vary with solar activity and with where you are on the planet. When they come through the atmosphere, these are secondary cosmic rays that have collisions with the things in the atmosphere. And we actually have to do some correction for barometric pressure. And then finally, they scatter when they hit hydrogen primarily at the ground surface. There's thermalization and absorption of these fast neutrons. So this is nothing that we're doing new. It's just that to mention that we do correct for these atmospheric conditions before using that count as a corrected neutron count. So our sensor is using what we call a corrected neutron count. This is just to show you on the left panel, we have, if you had dry earth versus water, that detection of the effect is seen up through the atmosphere. And importantly on the right, I'm just going to blow up that to show you, this is what they call the stopping power. You see that hydrogen is the dominant effect, but there are other things in the geology and the soils, carbon, that may have a small effect. This is a picture of the sensor in our field as well as a schematic. On the right, you can see that there's a distance effect. We talked about maybe 200 meters is a practical length that some of the early publications had this diameter going to 700, so 350 meters radius, but it does taper off. That's a radius where previous authors, this is right to determine that 86% of the signal came from there. The other point of this slide I wanted to make is it is well known that the wet, dry conditions affect the depth of penetration. So what we're measuring is changing with the moisture state. Actually, the footprint doesn't change too much. So this is then a family of curves for what we use to get volumetric moisture as a function of this corrected neutron count. And the N0 is a calibration parameter. So we need to measure in the field what's happening within that. And that has what looks like a fancy equation, but really it's mostly constants. And that N0 is our main calibration parameter. So we have moisture as a function of this N0 and then the dynamic neutron count. Darren Desilets has done some analyses and looked at uncertainty. You might call this accuracy, I might call it precision, but you can look at the standard deviation of the water content as a function of the mean water content and also of this N0. So what you see is that the volumetric water content, as it increases, our uncertainty also increases. Turning that around a little bit, I just made a plot here looking at our typical 3000 N0, and we can see that we get a volumetric water content. Again, this may be precision more than error, excuse me. Don't remember what else I wanted to say about that, but that's basically as you accumulate more counts, your error or your error goes down, your precision goes up, however you want to look at that. And we're really in that threshold where the curve gets very steep with many of our measurements. And so we'll talk about that. So this is our site, and you might be able to see the red dots. We do a radial pattern of point sampling. within the field. And these are what we use to calibrate the neutron sensor. And this is just an example table with the equation to show that you can get to that N0, and Peter's covering some of our data, but you can see that there are numbers for N0 that here look fairly consistent for the 15 and 30 centimeter depths. But I'll show you a full suite of data. So we went kind of overboard. We had a plan to do the 0 to 5 centimeter data on a regular basis for some modeling work. And we were able to use all these for the calibration of N0. So in the N0 column, I've shaded that just to show you where you can get higher and lower values over time, depending on the moisture state. And it does relate a bit to the soil water content is the right column in each of these. And you can see where it's wet and where it's dry. So here's a graph of those data looking at the calibrated N0. So that's the number that we're really caring about right now. And the mean soil moisture, this is from, excuse me, from the probe data. And you can see over all these data, for the 0 to 5, there's quite a trend. I don't fit a trend line because I don't think that's yet meaningful. But if you look at the 15 and 30 centimeter data, those are much flatter, which is what you would hope for, that our N0 is not varying a lot with the particular moisture state that we're sampling. So this is a range of those numbers, and going from 2,600 to 3,200 is quite a range. And we'll look at how that affects our uncertainty. And then you might say, well, that's not really fair to compare 5 centimeter to the 30 and 15 when we had a lot more dates. So I removed all of the dates that we did not have a 30 or 15, and this is what it looks like. So we still see more variability with the 5, but not quite as extreme. So this is the range of numbers that we see. Now we're looking 2,700 to 3,000. So again, bringing up this family of curves, what does this say about our uncertainty? So if we look for the 0 to 30, we're really looking in a zone like this. So for any particular calibration date, we could fall anywhere in this envelope. If we look at 0 to 15, it's biased a little higher, it gets a little bigger. 0 to 5, it's actually going biased lower. We have a lot more dry sample dates with that one. But I still think it's fair to say we might have gone out on any of the dates that we sampled. And this is the kind of uncertainty that we're dealing with. So it's really an important thing when you think about using these data. If you had a single calibration date, be careful. And then finally, just briefly, these are a half hour from our particular field site. And if you take time, okay, use this mic, is that better? If you do time period averaging, say a running average of 6 or 12 hours, this just shows that there's quite a bit of noise in these half-hour data. If we zoom in, you can see that that's not real. That's just a precision issue with this instrument because we're not accumulating enough counts. There's another example. And I'm almost done. So I won't reiterate all of this, but I think it raises a question about calibration and how we use the data, what our uncertainty is, and how should we as a community think about calibration, what would be a standard for that. And then if we're doing mobile studies, Jeff Neiman and I have a project, and he's going to talk a bit later, but we're concerned about how do you do this mapping of mobile cosmic ray with these issues in mind. So thank you. And I do have other stations to report later, but I didn't do it here. So thank you.